Okay, guys, so we're going through the last couple examples from chapter 9, section 3, which is talking about differential equations. So you may recall in the first example that we did, I talked about a separable differential equations, which is our focus in this chapter. So a separable differential equation is, of course, a equation that you can isolate the variables on each side of the equation. Okay, so let's take a look at this example. We have y prime of x equals e to the negative y times sine x. Okay, and so the first thing we're going to do is what we say, isolate each variable to the opposite sides. So I'm going to divide by e negative y, which is like multiplying by e to the y power. So we end up with something like this. Okay, e to the y power becomes positive at the top of the fraction. And then I'm going to replace my y prime here with a different notation that's a little more helpful. So I'm going to rewrite this as dy over dx. Okay, and that's just to make this next step a little bit simpler. Okay, and that's going to equal sine x. Okay, and what we'll do now is we can take this dx and we can multiply it to this side, and now you can see all the y terminology is on the left side and all the x's are on the right side. Okay, and at this point we are ready to set up our integral, so we can say e to the y dy equals integral sine x dx. Okay, now I will say that this step is commonly assumed, and you don't really need to take the time to do that. Okay, and so a lot of people will not change y prime into dy dx, but it is helpful to see it the first couple of times that we do this. Okay, so now let's continue to finish out this problem. So once we take the integral of this, you're going to see that this is going to lead us to e to the y, and on the right side we have negative cosine x, okay, plus c. Now note, we don't need to plus c on both sides. One constant is enough, because adding c to both sides is kind of redundant and it kind of does the same thing twice. Okay, now with this, we have the general solution. Okay, and what we can do is we can rewrite this to be in terms of y if we want. So we could make this by taking the natural log, y equals ln negative cosine x plus c. Okay, and if we want to make the specific solutions, we can use the points they gave us above to try and solve for c. So we could use, like, these three coordinates are what, 0, 1, there's pi over 2, 1/2, and pi ln 2. Okay, so you could plug any of these in for x and y to solve c. And we can do one of them. We'll do 0, 1 really quickly because it's pretty straightforward. And so, an example, if we say 1 is y, so equals ln negative cosine 0 plus c. Cosine of 0 is, of course, just 1. So this is negative 1 plus c ln equals 1. Okay, and then basically what we'll discover is that this is going to end up being c equals e plus 1. So you could repeat this process with the other coordinates that we were given, like pi over 2 and 1/2 and pi and natural log 2. And this right here is our specific solution, which refers to having that c value solved out. Okay, so this is the general idea. I always say that it is a double I technique, which is you first isolate your variables and then you take the integral of it. Okay, the differentials that we're working on are all called separable equations, which means that it is always possible to isolate the variables. Okay, let's look at one more where we've again been given an initial value problem. Okay, so here is the equation, and they also give us an initial value, which is y of 0 equals pi over 6. So this time we will solve it, and we only have to do it once. They have one initial value condition given. Okay, so let's take a look at where this takes us. These are already separated, kindly enough. So then we don't need to rearrange anything. We're basically ready for the integral step at this point. So what we will end up with is something like this. Integral of cosine y dy equals integral sine squared t cosine t dt. Now notice I skipped that step that I showed you originally where I rewrote y prime of t as dy dt and moved the dt over. We've kind of assumed that step and we're going to work through it as such, okay? So left hand side, very easy. This is actually just sine y. Okay, again, I'm going to save the plus c for the right-hand side. You can technically put it on either side, but it's more common to put it on the non-y variable. Okay, so on this side, we actually have to use u substitution. So this is going to be u squared, and cosine t dt will be du. Okay, so this leads us to u cubed over 3 plus c, which is sine cubed t over 3 plus c. Okay, now from here, let's use the information they gave us up here to solve for c. Okay, so again, what I have currently is called a general solution, but when we solve for c, we can call that a specific solution. Okay, so let's plug in what we know. So sine pi over 6 equals sine cubed 0 over 3 plus c. Okay, we get 1/2 equals 0 plus c, so c equals to 1/2. Okay, and my specific solution using this is going to be the same equation just filled in with that c value. Okay, and so this right here that I just boxed off is my specific solution. Okay, whereas what I came up with here in blue is a general solution. And again, the difference is that in the general solution, you're going to have that c built in, and in the specific solution, you're going to have solved for the c. Okay, now you could write this as a y equals equation. You can use an arc sine and say y equals arc sine of that remaining part of the equation to get it by itself. It's not necessary in this case to do so because it does make the equation uglier. But if it's easy to get the y by itself, you can very conveniently do so. But in some cases, it's totally okay to leave your answer like this. Okay, so I hope you found these two examples helpful. Good luck and happy studying.